Hello everybody and welcome to Chapter 10, Section 7 on the complex numbers. This section we would like to introduce the idea of complex numbers and imaginary numbers. So let's take a look. Here we have an imaginary number. So we denote the imaginary number by the letter I, and we define this to be the square root of -1. Also, by this definition, we know the fact then that I squared, which is going to be the square root of -1 times the square root of -1, is just going to be -1. All right, so now, based upon what we just talked about with this imaginary number, an imaginary number then allows us to take square roots, or in particular, or in general, I should say, even roots of negative numbers. So let's just recall before we could not take the square root of -4 in the real numbers because we cannot take even roots of negative numbers. They do not return a real number. So we have to take the real numbers and extend the real numbers to include imaginary numbers. And no, I have no idea why it's called a real number and an imaginary number, but it does kind of sound like a La La Land fairy tale. I get it. So some examples. So let's just note that in the long run, the square root of -4, we can rewrite this as the square root of -1 times the square root of 4. And the square root of -1 by definition is I, and the square root of 4 is 2. So at the end of the day, we just call this 2I. So when we extend into the imaginary realm, the square root of -4 is now computable, or we can compute the square root of -4, and we know that's going to equal to 2I. So the square root of -7 then, well, the negative comes out of the square root now as an I, so that leaves us with the square root of 7. So technically we should write this as the square root of 7 and then the letter I. So let's just note that the square root of -18, well, the negative can come out of the square root as an I, so that leaves us with a -18 on the inside. But -18 can be rewritten as the square root of 9 times 2, and 9 can come out of the square root as a 3. So we have this 3 root 2 and then our I. It's kind of customary to kind of put the I towards the end or at the end. So the square root of 45, well, let's just recall 45 is 9 times 5. 9 comes out of the square root as 3. The negative comes out as an I, so we get 3I square root of 5. Okay, when we pull everything out of the square root, so our final answer would be 3 root 5I. Okay? So complex numbers. So now we got real numbers. Now we've got imaginary numbers. So guess what? We put both of these together and we have what is called a complex number. And a complex number is just taking a real component along with an imaginary component. So for the complex number, we usually write this in the form A plus BI, A plus or minus BI, just depends on that AB, and AB is technically real numbers. Okay, so A is known as the real component and the BI is the imaginary component. So for example, we have this 2 minus 3I, where 2 is the real component and the -3I is the imaginary component. If we take a look at just any real number, in particular 3, notice that we can write this as, in its complex form, as 3 plus 0I. So, believe it or not, we have been dealing with complex numbers already. It's just that the I component, the imaginary component, has just a coefficient of 0. For example, now 4I, well, 4I can be rewritten in its complex form as 0 because the real component would be the number 0 and then plus 4I. So we can take any real number and write it as a complex number, any imaginary number, and rewrite it as a complex numbers. So to add and subtract complex numbers, which is going to be the next thing, all right, we would like to take any two complex numbers and add them. And basically the bottom line is we just take and add the real components together, and then we add the imaginary components together. So no matter if we're adding or subtracting. Thus, a plus or minus c di, a plus bi, and then c plus di, we just take and do the a plus or minus the c, depending on what's in the middle, and then the bi plus or minus the d. Okay, so we just add the real numbers together, add the imaginary numbers together. That's what it boils down to. So notice we have 2 plus 3i plus negative 3 plus 2i. So notice to put the real components together, here we have the 2 and the negative 3, so I put them right there. And then we have the 3i plus the 2i, and so I've just put them right there. So notice that 2 minus 3 is negative 1. 3i plus 2i is a total of 5i. So here we're going to subtract. So again, we have 3 minus 5i, and then we want to subtract 2 plus 3i. So notice here it just becomes adding the real numbers or subtracting. So 3 minus 2, that's where this 1 comes from. And then notice here we have negative 5 minus 3i. So negative 5i minus 3i gives us a grand total of negative 8i. So our final answer is 1 minus 8i. In this case, we have 4i minus the quantity 3 minus I. So for the 4i, let's just note that the real component is just 0. So notice we can go ahead and distribute that subtraction sign across. So I get 4i minus 3 plus I. Combining the real and the imaginary components together, I get a negative 3. So I'll just bring this negative 3 on down to here. And then 4i plus I gives me a grand total of 5i. So multiplying complex numbers, well, we just have to remember a couple of little things. All right, so with complex numbers, we just have to remember I squared is equal to negative 1. And we also have the fact that I is equal to the square root of negative 1. So let's just note here, if I take this imaginary component here, negative 4i times 5i, negative 4 times 5, gives me my negative 20. And let's just note I times I gives me the I squared. So I bring my negative 20 down here, and we can recall that I squared is negative 1. So we get negative 20 times negative 1, and we get a positive 20. So let's just note we have 5i times 2 plus I. So again, 5i times 2, well, that gives me my 10i. And then 5i all the way over to this I gives us 5i squared. So the 10i comes down, and let's just recall that I squared is negative 1. So we get 10i minus 5. So this is equal to negative 5 plus 10i. Again, it's to put it in that a plus bi form. And then finally here we have 9 plus 2i times 2 plus 3i. So let's just recall we just have to note and do our FOIL. So let's note that 9 times 2 is 18. 9 times 3i is 27i. 2i times 2 is 4i. And 2i times 3i is 6i squared. So notice here we can bring the 18 down. 27i plus 4i is 31i. And we know that I squared is negative 1. So 6i squared now becomes minus 6. So 18 minus 6 is 12. And then the 31i just comes down. So at the end of the day, 9 plus 2i times 2 plus 3i is 12 plus 31i. So let's recall conjugate binomials for our division of complex numbers. So let's just recall that we talked about a plus bi. Well, this has a conjugate of a minus bi. Remembering that the word conjugate means similar but different. So in our complex numbers, we have the fact that a plus bi is kind of a binomial in form. So the complex conjugate in this case, complex conjugate is a minus bi. So a plus bi and a minus bi are complex conjugates of one another. So let's see what happens when I take a plus bi and multiply it by its conjugate. So again, using our FOIL method, we get a times a gives us a squared, and then a times a minus bi gives us a minus abi. Bi times a gives us abi, just rearranging the letters, and then bi times a minus bi gives us a minus b squared, I squared. And let's just note that these middle terms drop out, they subtract out, so we left with a squared minus b squared I squared, which we know that I squared is negative 1. So this all reduces down to a squared plus b squared. So all we have to do now is when we product complex conjugates together, we just take the a part and square it, and just pull off that b part and square it, except now we have to add those two numbers together. So let's see this in action. Okay, so here we have 9 plus 7i, and we divide this by 1 plus 7, or 1 plus I. So the idea, what we do is, just like we were doing with radicals, the idea was to multiply by the conjugate binomial. To remove the radicals, what we're going to do is multiply by the complex conjugate and get rid of the imaginary component. So notice if I take and multiply the complex conjugate of 1 plus I is 1 minus I, and when I multiply the bottom, I have to multiply the top. So notice if I FOIL the top, I get 9 times 1, so that gives me 9. And then 9 times minus a is minus 9i. 7i times 1 is 7i. And note that 7i times a minus I is 7i squared. And notice that since we're just taking 1 plus I times 1 minus I, its complex conjugate, all I have to do is take this 1 and bring it down squared, and then I just bring this down, and the coefficient here is 1, so I get this 1. So now we just clean up the top here. So cleaning up the top, so I bring down this 9, and then minus 9i plus 7i gives me a grand total of negative 2i. And let's just note that I squared is negative 1, so this comes down as plus 7. So 9 plus 7 is 16. Minus 2i divided by 2, and notice that I can factor a 2 out of the top, so this leaves us with 8 minus I. The idea now is that we have to put this in the form a plus or a minus bi. We always put it in that form. Technically, we don't leave it in this form. So 16 over 2 is 8, minus comes down, 2i divided by 2 just gives us our I. Taking a look at one more, so 5 minus I divided by 3 minus 2i. So let's just note that the complex conjugate of the denominator is 3 plus 2i. So here we'll multiply the top and the bottom by 3 plus 2i. So let's just note that 5 times 3, foiling the top, 5 times 3 is 15. 5 times 2i is our 10i. Negative I times 3 is minus 3i. And negative I times 2i is a minus 2i squared. And again, we just bring the 3 down and square it. And then just bring that number 2 down and square it. So I get 9 plus 4. Now for the top, we'll clean up the top. Let's just note that we can combine 10i minus 3i. So the 15 comes down for the ride. 10i minus 3i is our 7i. I squared is negative 1. So negative 2 times the negative 1. So this becomes plus 2. 9 plus 4 is 13. All right. And the last thing to do, we clean up the top. So hopefully we can all see we get 15 plus 2 is 17 plus 7i divided by 13. So again, to put this, the instructions will say to put it in a plus bi form. All we do is break that apart and write this as 17 over 13 plus 7 over 13i. For our last topic, let's just note some powers of I. So I is defined to be the square root of negative 1. So I squared is the square root of negative 1 squared, which is negative 1. I cubed is I squared times I, but we know that I squared is negative 1, so I cubed is negative I. And then I to the fourth is I squared times I squared, which is negative 1, times negative 1, which is 1. And then it's interesting to note that if we rewrite I to the fifth as I to the fourth times I to the fourth is 1, I is the square root of negative 1, so I to the fifth, notice, becomes exactly the square root of negative 1. Let's just note that I to the sixth is I to the fourth times I squared. I to the fourth is 1, I squared is negative 1, and 1 times negative 1 is negative 1. So notice that I to the sixth becomes negative 1. I to the seventh, you'll probably can guess, becomes negative I, and I to the eighth becomes 1. So this thing cycles through, and it takes fours. It goes in fours. 1. So I to the sixth, I to the seventh, I to the eighth, I to the ninth, I to the 10th, I to the 11th, I to the 12th, and so forth. I believe that there is a page in the textbook. In fact, I have it right here at the bottom of page 647. Really no need to memorize that. So how do we deal with powers of I? Well, I would say just try to rewrite these as many times as you can involving I to the fourth, because I to the fourth is just 1. So let's just note that I to the eighth is nothing more than I to the fourth times I to the fourth. Remember, with like bases, we add the exponents. I to the fourth is 1, so it's 1 times 1 equals 1. Let's just note that I to the 21, well, I to the 21 is I to the 20th times I, and I to the 20th, I can rewrite that as A to the fourth raised to the fifth power, which we know that I to the fourth is 1, so this becomes 1 to the fifth power times, and then this I comes along here, and 1 to the fifth power is just 1, I, so I to the 21st power is just I. So this is kind of what we do, is we just kind of play this. How can I rewrite this where I can use rules of exponents? Let's just note you could have wrote I to the fourth times 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 I to the fourth, and then times I, and then note you would have had those 5 I to the fourths as just 1. Let's note that I to the 15th then is I to the 12th times I cubed. I to the 12th, this one here is my 4, so 4 times 3 using my rules of exponents. So I to the fourth to the cube, I to the fourth we know is 1. 1 cubed is still 1. I cubed we already know is negative I. So this all crunches out to negative I. Then for our last example, we got I to the 40th. Well, I to the 40th, hopefully we can see, is nothing more than I to the fourth raised to the 10th power, because I multiply these exponents here. All right, so I to the fourth is 1, so 1 to the 10th, so I to the 40th is just 1. So that is our last section in chapter 10, everything you wanted to know about complex numbers. So we got imaginaries, we have complex numbers, we can add, subtract, multiply complex numbers. The only thing we have to recall with multiplying is that I squared is -1. And then working with division, we don't really technically divide. All we do really is multiply by the complex conjugate of the denominator. So if you have any muddy points, please let me know in our warm-up. Outside of that, I will see you in class, and we will handle some of these, and I'll have you doing some add, subtract, multiply, divide, and finding imaginary numbers. Outside of that, have a great day.